Okay, good morning, everyone. Let's start. Welcome to the Warren Lecture Series. And today is this very special occasion, which we would all like to have more and more often, where we are greeting our former student, now associate professor at the Georgia Tech, Haiying Huang. And Haiying is, this is success story. Haiying was discovered by Charles Forhurst on his scouting trip to China, brought to Minnesota, and got right to the group of Emmanuel de Ternay when he had a group of outstanding students. They were very close together. And she defended her PhD in 1999 very successfully, and then she got a job at Houston and Schlumberger in Houston, and working in Schlumberger for 6 years. After that, she started her academic career in Georgia Tech right away, where she is now. She started, of course, as an assistant professor, but now Haiying is an associate professor. So Haiying is a wonderful person, my personal friend. She is very loyal to her school, to her friends, colleagues, and please join me in welcoming Haiying home.
Thank you all. It's so great to be back. The topic of my presentation, it reads a little bit lengthy, but it's a problem actually I discovered when at the end of my PhD study. And I cannot deny that problem has not bothered me. So after all these years, I'm glad I have found a solution and to overcome the problem. And what exactly was that? So I'm pretty sure this audience will be very familiar with the method of discrete element approach. And you try to model the solid behavior using collections of particles. And for cohesive material, you can try to bond the particles. And so the conventional DEM approach uses soft contact spherical particles, dense packing, short-range interactions, and very common, we use elasto-perfectly brittle type of contact. And as a result, the failure envelope, if you plot them in the principal stress space, sigma 1 versus sigma 3, you end up with a slope about around 4, and that's the maximum you can get. And not only that, it misses the nonlinearity around the confined extension range completely. So it went straight to linearly to the tensile strength. So for a while, we didn't know what to do. And it wasn't a problem for us only. Many other DEM code also have the same problem. So if we plot the compressive strength over tensile strength, it would be a function of the bond strength ratio. So this is a main parameter that governs the bond strength ratio. And the TS in this case is a shear bond strength. The TN is normal bond stress. So when the shear bond strength is small, so all the failure is governed by shear, so it ends up being around slightly above 1. When the shear bond strength is large, normal bond strength is small, then everything ends up being governed by the normal bond failure. So again, as I said, the maximum you can get is about 4. And that's a 2D simulation. 3D, the number slightly varies, but it's still the same. For real rock, this number, of course, is much smaller. The numerical number is much smaller. The real rock strength ratio would be much higher. As you can see from a compilation on this table, the number ranges from about 13 something to all the way to 30. And the failure envelope over here is very stiff, highly nonlinear. Most of the time, people measure only this part, and you feed through by a more Coulomb failure line, could be approximated by a linear behavior. But if you extrapolate to the confined extension range, here, the numerical approach missed it completely. So the problem's been there, and the people have been trying different approach, and one of the approach quite successful was to clump particles. In other words, you make these particles, those collection, a small group of particles, a big grain, and then constrain the rotations of the grains. So with the constraint of rotation, your compressive strength goes up significantly. And when you pull it apart in uniaxial tension, whether you constrain the rotation or no rotation, more or less the number remains the same. So as a result, then your uniaxial compressive strength over tensile strength could increase significantly. But in this case, you are using more particles to simulate just one grain. In other words, as a result, your number of particles to model properly the behavior would need to increase quite a bit. In Itasca, Dave Portiondi has also worked on approach and what he called a grain-based method. So in this case, you are laying over another type of contact on top of the particles. So basically, by introducing these flat joints, then you are having, in a way, that's a multi-scaled representation of the particle assembly. And with that, the strength ratio could also increase, because that's like introducing the granularity into the system. People have also been trying to increase the interaction range. So remember, the conventional approach we use is the so-called soft contact. Only when they are in contact, we say, okay, there's contact force in between these two particles. So this group of people, when they look at the contact, they say, okay, even if they are far apart, we still consider them in contact and therefore assign them contact forces. And by doing so, you basically increase the coordination number. So with the increase in the coordination number, the strength ratio could also increase in the range, becomes very realistic. So if we look back all these approach, it's either the shape of the particles or the interaction range or the coordination number, and or introduce the granularity of to the system. So these elements could contribute to the increase of the strength ratio. So we have been thinking for materials like sandstone. So for approaches like this, the grain-based method, it's perhaps very suited for materials like granite, because the grain sizes are quite large. But I was thinking for materials like sandstone, basically it's pure quartz with a little bit of cementation. And the question is, why do we need to introduce a different layer, a grain structure on top of the particle? And why can we not just manipulate the contact laws to achieve that? So we thought about using the displacement-softening contact model. But the story now, as I tell it, it seems straightforward, but really it wasn't really that smooth. Because actually, when I was a student, my office mate, Branko Dominiak, had already wrote a contact law that has a softening portion. And back then, we just look at it, the effect of this softening law on the toughness of the particle assembly. And we know with more softening, you get higher toughness. And never back then, we were thinking how the toughness, how the softening would affect the compressive behavior. We never really make the connection between compression test and the softening behavior. We were always thinking process zone softening, process zone, and therefore toughness, trying to get something out of the tensile strength. So this time, when Joe has been doing quite a bit of work in measuring the size of the process zone in three-point banding, and so I was wondering how along that line what the process zone would look like. And so for the sake of getting the process zone, I have to put this displacement softening law, and therefore that's why we said, okay, go back and we get the softening law back into PFC, and we'll see what happens. So the conventional contact model in PFC, particle flow code, is just elasto-perfect plastic. So the contact force reaches a maximum and drops to 0. And you could have different types of contact on top of each other. You can have the point contact, basically the particle-particle contact. In that case, it's just elastic frictional. There's no bonding in between. And you can have the area contact, basically sort of like mimics the cementation. And in that, you can have bonds. And that's where we implement our softening law. So the softening law, at the moment, to begin with, we just implement that to the normal component. And the reason being, I don't want to do as many parameters as they are messy. And I want to see exactly what this softening branch or softening law will do to the material behavior. So, so therefore, I assume the shear component is there, the shear failure is there, and we have nice results regarding the shear bond failure. But at the moment, I'll just show you how the normal component softening will do to the material behavior. So I'm assuming, all the result here, I'm assuming the shear bond strength is much larger than the normal bond strength, so they don't break in. The failure criterion is not based on shear component, but the shear component, the shear force will drop to 0 when the bond fails. So the bonding, the failure criterion over here, we constructed in a way in terms of stretch of the bond. The bond stretch, when it reaches to a critical displacement that's here, then we say the bond has failed. And in that case, we are assuming the bond is sort of like a beam, so it has a stretch on along the neutral axis, and there's a contribution from the moment. And the only parameter, the new parameter we added to it is we call the softening coefficient. And that's the unloading stiffness over the loading stiffness. So the unloading stiffness and this loading stiffness. This is the only new parameter we added to the parallel bond contact model that's in PFC. So we conducted both two-dimensional and three-dimensional uniaxial test to see what the uniaxial compressive strength and the tensile strength would be, how would that be like. So these are basic parameters. And the thing we, if you look at softening laws, so then failure will be related to the energy that you can compute underneath this curve. So if we just fix the bond strength over here, and if we decrease the softening coefficient, then we'll end up with the uniaxial compressive strength larger and larger. And as a result, the simulation time will be much longer. So my student thought of a clever way, and at least in a way he could save some time in the office, or the computer could save some time. So instead of just fixing the bond strength, he decided to fix that the nominal energy associated with the one bond breakage. That's basically the area underneath that softening curve. And so once that area is fixed, then we pick a bond strength. The first one that's a baseline would be related to the elasto-brittle material, elasto-brittle contact. That corresponds to the beta equal to infinity. And we fix this number, in other words, this number, and then we translate based on the energy being the energy density being constant. Then we compute the bond strengths for different number of softening coefficient. So we chose 3 particular cases to look at it. A very small softening coefficient, nearly, you can think of it as nearly elasto-perfect plastic, and a moderate one, and an infinity. Infinity is, again, the baseline of elasto-perfect brittle material. So again, the bond strength is changing with these 3 softening coefficient. As it increases, the bond strength decreases. So my thinking first, to begin with, I was to think, okay, the bond strength increases, then the strength would go together with the bond strength, it would increase as well. Well, that is true for the uniaxial tensile strength. So uniaxial tensile strength, the peak, the peak actually goes together with increases with the bond strength. So the bond strength increases from 6, 15, 50, and that increases as the beta increases. But it wasn't true for the compressive strength. So the stress strain, if you look at it, that's the beta with the highest bond strength, and that end up with the lowest compressive strength. And beta with 0.15, that has bond strength of 6, but that one has the highest strength. So that requires a little bit of explanation. So that was, the result was 2D, and those are 3D results. And more or less, we get the similar behavior, except that with 3D now we have actually quite significant strain hardening in the pre-peak area for the beta. That's very small coefficient. In other words, significant softening. So when you stretch it, the bond in the domains, most of them have been in softening. That's why it's contributing to that long range of ductility. But here, all these parameters, I think these behaviors can be tuned. The reason I didn't do anything at this point is only because I want to compare only this parameter. So now that's a summary of the strength we get and the strength ratio. So if we look at the strength ratio, the infinite case, the elasto-perfect brittle, still about 4 in 3D. But for the very small beta, significant softening, we get the strength ratio over 30. That's very, very high. And again, in the beginning, I was very surprised. Now, if we plot we did, of course, more than 3 cases. And if we plot, summarize the strength ratio as a function of beta, you can see it starts from around 35 something and went down. And there is a range of beta where the strength ratio is actually not changing. What does that mean over here? Well, this means I'm pretty sure here everybody is familiar with the concept of a testing machine. So you need a stiff testing machine to get the strength of material, to get the behavior of material. So in your system, when you have a sample and the machine, the behavior is governed by the softer ones. So in this case, if you are putting a very stiff unloading path, then what it means, the unloading is governed by the neighborhood, by the system. Therefore, your softening path, or even when you go to the brittle mode, your unloading is not following the softening path you prescribed, is following the behavior of the system. And therefore, whatever you put in is ineffective. And actually, when I go back to the literature, I've seen softening laws being presented in some of the papers in regarding to contact laws, and nobody really came up with this ratio that high. They were still in that range. So I suspected that even if people put in some numbers, sometimes they were probably just exploring the range over here, and therefore they didn't realize actually the softening laws, they're working actually to help them to get the high strength ratio. So, but if you go down really low, around if it is smaller, around 3.5, now the softening law is actually taking effect. And it could bring your strength ratio to quite realistic numbers. And as I said, we need a little bit of explanation is needed to understand why with what we prescribed, the bond strength increasing with the beta, but the strength in the compressive strength actually decreases. So if you look at the crack number, the micro crack number, the micro cracks are so if a bond breaks, we refer that to a micro crack event. So if you look at the peak, in uniaxial tension, there's barely any cracks, micro cracks at the peak. So the peak at uniaxial tension is actually at the moment when the system hasn't really cracked. There are only a few tiny ones, and then after that, all the cracks would the through crack would be developed afterwards over in the post-peak area. Now, if you look at uniaxial compression at the peak, so 67, 200 something, and over 300, that means there is progressive failure prior to the peak. So the bond has been broken and energy dissipated significantly. Significant energy dissipation has taken place prior to the peak. So therefore, we could think about, for the tension test, the bond strength is a primary factor. But for the compression test, it would be the total number of cracks times the nominal energy as a dissipation, and that would be the primary factor. So this is, again, I showed you the curves and numbers with, for 2D, but for 3D, it's the same thing. There's a significant contrast in the number of cracks you observe in tension and in compression. Of course, it has to do with the failure mechanism as well, because tensile failure is just one single crack. With compression, you develop shear bands, and not only one, it could be multiple bands as well. And to validate my point about the uniaxial tensile strength is more related to the bond strength, and the uniaxial compressive strength is more related to the total energy loss. This is more related to the nominal energy loss times the total number of cracks. We can look at the number of softening bound, the percentage of softening bound that, and as a function of a degree of damage or degree of softening. 1 means it's right at the moment when the softening starts. 0. 1 means the bond has reached the failure criterion, it's ready to fail. In direct tension, you see most of the bonds, over 80%, with only slight damage. In other words, we are right after, that's plotted at the tip, at the peak. That means most of the bonds in softening, they are just having they are only, if we go back to the contact law, most of them are only here. They haven't reached to this part yet. But on the other hand, for compression test, you see this now, the percentage of percentage of the bonds with light damage is now decreased to 60%, but there is a tail. There is a tail of bonds that with various degree of damage and all the way to very significant damage. Okay, so that means if we go back again to the contact law, that means in compression test, a lot of bonds are situated at the peak. They are situated in this range, but in compression test, most of them are here, and that's why I would like to make the assertion that the tensile strength is more governed by the bond strength over here, but the compression strength would be related to the area that's underneath this curve. And because the area underneath the curve is constant, and is constant for different beta, and only the number of cracks would be the different outcome for these three cases. So beta with a lower beta, you see the number of cracks is much larger than the number of cracks for the perfect brittle case. And therefore, it's reasonable to see, it's not surprising to see the compressive strength actually increases when the beta is actually decreasing and the bond strength is decreasing. So I hope I've convinced you that that this softening law, by implementing a softening law, actually you can have interestingly could have realistic behaviors of rocks. Now the question is, we have this parameter beta. So from the point of view of numerical simulation, everybody knows the calibration of material parameters is quite messy. So will this beta be particle size dependent? Is this true? Remember, I also showed you the threshold case when the beta is lower than 3.5, about 3.5, then the beta becomes effective. So is this number particle size dependent? And if it is particle size dependent, that means my simulation result is only true for my set of simulation. I cannot really extrapolate my result, this 3.5, or in general, whatever beta number in association to the strength ratio wouldn't be, you cannot generalize these kind of results. Well, if we look at the list of parameters we have, so this would be the bond strength ratio, our shear bond over normal bond, and this would be the deviation in the normal bond strength, deviation in the shear bond strength, and that's bond strength over the stiffness or modulus. That's a modulus ratio between the area and the point and the area in the contrast of that. These are the stiffness ratios related to the point contact and the area contact. And then there are parameters related to discretization, aspect ratio, porosity. So this beta over here, and beta is a dimensionless parameter because we define it as a strength ratio, the stiffness ratio between the softening one and the loading one. So basically, based on dimensional analysis, if you assume it's a quasi-static loading, fine discretization, your strength could be written in such an expression. And it turns out, so then if we are not talking about stiffness, we're talking about only strength, this beta and this bond strength ratio are the two primary factors affecting the strength. And in our simulation, in the result I just presented to you, the shear bond strength over normal bond strength, I set it to very large, so this one goes away, and that means beta is the only primary factor affecting this strength ratio. So that's good news. Also, if you look at these list of parameters, the length only comes in form of that will be characterization of particle size distribution, and we are assuming the discretization is fine enough. So if we look at this list of parameters and this scaling form, that means the strength ratio, a variation of strength ratio with beta, if you take this one divided by this one, is actually not dependent on the particle size. So that means the threshold beta I was talking about and the behaviors of the strength ratio as a function of beta is also quite generic. If you change, for example, stiffness ratio or the bond strength over the stiffness ratio, this will change, of course, slightly. But hopefully within the material, for the materials we are dealing with, like concrete and rock, this parameter is not that, it won't change that significantly, and therefore the curve I got, we can actually extrapolate. In other words, the ratio of strength ratio, the strength ratio as a function of beta, the curve I just showed you, it will change slightly. If you change parameters such as those, it will. But the order of magnitude or the global behavior, the overall trend, dependence of the strength ratio as a function of beta, it would still be the same. So what I presented to you, it's in the ballpark. It will be true for everything, for all the kind of parameters you are going to simulate for rocks or concrete. So I'll just show you some of the. Sometime when you try to play with contact laws, you could actually mess up the failure behaviors. And you may not necessarily produce, for example, a shear band. You end up with a bulging type of a failure. So in that case, then the contact law is not doing its job. So I just want to make sure, indeed, we'll produce the failure mechanism that's consistent with the experiment. And in this case, if you look at uniaxial tension, so it's one single mode 1 crack, and the color indicates time. So the blue one over here, that means the earliest crack, and the brown or dark red means the late time. And 60% of in the post-peak means it's after the peak, the load level is 60% of the strength. So by manipulating this, the softening laws, we are not changing the mode 1 type of failure mechanism. And for uniaxial compression, elasto-perfect brittle, you see this shear band over here. And as the softening coefficient decreases, you still see also informal shear band. So overall, the failure mechanism hasn't been changed. Now, there are some very interesting observations. I believe it's perhaps the first time observed numerically. We've been using tensile cut in combination with the more Coulomb failure criterion to model rocks and concrete. So the justification came from experiments. For example, Breeze in the 60s, they've done experiment and showed the tensile cut is justified. And the original Griffith's theory, it proposed that the material would fail in tension if the principal compressive stress is about 3 times, no more than 3 times of the tensile principal stress. And that's for 2D plane strain. For 3D, I believe the modified Griffith's criteria is about 7 to 8 times. Now, if we look at our result, so here, we also conducted a confined a Tri-Axial compression and confined extension test. So this could be fitted very nicely with the Hooke-Brown criterion. Now, but if we zoom in the confined extension range, what we found is that these dots are from the simulation. The filled ones are 2D, and the empty ones are 3D. You can more or less conclude when the confining stress, in that case, is the sigma 1 would be the confining stress for the confined extension test. That's compression. And the sigma 3 is the direction that's in tension. So you can say that with the confined extension, the maximum tensile criterion is actually still true. For 2D is perhaps up to about confining pressure about 20, and the tensile strength over here is around 6 and 7. So 20 divided by 6 and 7, it's in the ballpark of 2 and 3 for 2D. For 3D, all the way up about, you can say perhaps slightly less than 60, and your tensile strength being 6 and 7, it's about 7, 8 times. So I was actually very surprised that with numerical simulation, we are actually producing results consistent going all the way back to those from Griffiths. And I'll just give you a summary of the fitting parameters. And as you can see, we are picking the particular case with beta equals to 0.1 to do the confined tri-axial compression and confined extension simulation. And the friction coefficient, if you fit it, it's about 41 and 30. So the friction coefficient, that means only fitting the compression side. And that one, you see, this is not really outrageously different from the regular rock we've been dealing with. But the good news is that now we can have the compressive strength, the strength ratio being very reasonable, much larger than the 4, 5, 3 that we've been dealing with the just conventional parallel bond. And it's also interesting to see how the failure evolves from a single crack that's mode 1 to shear band in all the way from uniaxial tension to confined extension to tri-axial compression. So basically, what it shows over here, it seems the mechanism of transition from mode 1 crack to a shear band is through these development of an echelon crack. So in mode 1, in uniaxial tension, they are very localized. When you have compression, when you have compressive stress on the side, then these seed cracks would start to develop parallel to sigma 1, but they are scattered. And then those become linked, and so those step-like features. So for example, here, 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 and then they get linked, becomes a step going up and a step. That seems to be providing a mechanism for transition from mode 1 crack to a shear band. These two, because of the way the simulation is set up, you really need to really need to flip them 90 degrees to compare these two with the other three. So these are whatever I presented are just made up numbers. I just want to see the beta, how it affects the material behavior in terms of in particular the failure envelope and the strength ratio. Now, in the literature, most of the time when people try to calibrate their contact models, these two seems to be the benchmark. So I decided to take that challenge and try to see whether we can match those the parameters of these two rocks, granite and Barre sandstone, and these are the numbers I found in the literature. And the Ladue-Burnett granite, because of the URL project in Canada, it's been very extensively studied. So all these experimental data, as I got from the thesis of Derek Martin, and the simulation results. So the 2Ds, triangles are 2D, and the circles, filled circles are 3D. So in other words, these are our simulation results, and these are the 3D simulation results. The 3D shows a failure envelope that's below the 2D one, and that's not surprising because in 2D simulation, it's neither plane strain nor plane stress. It's sort of confined. But even with plane strain, you have only one dimension that of displacement, the lateral displacement. In 3D, you have two-dimensional, you have two directions for lateral displacement. That's why the failure mechanisms, the failures envelopes are actually lower than the 2D one. And in this case, the 3D simulation, just, there's a discrepancy between the simulation and the experiment. But I'm not surprised by that because the granite, the grain size is so large and the granite's very angular. And we are just using spheres to approximate that. So I expected, for example, the flat joint model would certainly do a better job than what we have proposed for just a circular particle, or spherical particle. Now with sandstone, now here we can see it's actually very nice match. The sandstone results are from a master student of from Texas A&M in a Chester's group. And the failure envelope we fit for the experiment is actually overlapping with our simulation fit. There is a dashed blue line, you barely see it underneath. So that's how good the fit is. So with that, I hope that I've convinced you that we have a nice, interesting model that could capture the rock behavior, failure behaviors quite nicely. And just for fun, these are the three-dimensional failure mechanism. So if it is confined, now you don't just get if the confinement's quite no longer small, you see the wavy shape of this crack, like potato chips. For three-dimensional, the shear band is not only just a single band or a plane, it's actually a spiral kind of shape. So it's, the trace would be helical. And of course, if these are internal reactions. So if you, in the lab, when you observe, you of course cannot observe any structures like this. But most of the time when you fail it, compression test, you have a conical structure of those samples. That will be consistent with this type of failure, what I plotted over here. Now, there are interesting implications about now that we can model the material with higher strength ratio. So if we just have the perfectly brittle contact law, so this is Brazilian test, and the load was applied at the top and bottom. And again, those plots are micro cracks. Color indicates time. If you just have the elasto-perfect brittle contact laws, what you observe is the crack would start from the loading area and a cluster of them, so you can interpret that as a plastic zone. And then growth of the plastic zone would drive the development of tensile cracks. So this is similar to indentation type of failure. So again, with a perfect brittle law, you have this indentation type of failure. But for tensile, for Brazilian test to be, the interpretation of Brazilian test really is to assume, the premise for that was that to assume you actually have a center crack. A crack develops in the center, goes both ways, and because the elastic solution would tell you in the center, there's nearly uniform tensile stress, although it's confined. And so, in other words, what you can conclude, if you have a elasto-perfect brittle contact laws, you cannot actually produce this center crack type of behavior. And only when you have very low beta, so the parameter over here, the first one is beta, the second one is the diameter of the sample in millimeter. Only when you have a low beta that is high strength ratio, you actually could observe a tensile crack. So that's 2D simulation. And 3D, it's the same as well. So when you have a lower beta, that means high strength ratio, you have the center crack developed. All of them are plotted around the peak of the force displacement curve. Okay? And if you read this row, that is the simulations with elasto-perfect brittle contact loss, all of them you see it's driving from the loading area towards the center. So that means there are two types of primary types of failure scenarios. One is indentation type, and that over here I call it a scenario, actually the indentation type I call it scenario 2, and the first type I call it scenario 1. So the failure mechanism actually depends on beta, that means the strength ratio, and also the particle, the sample size as well. And if we go back, if you have a larger sample size, actually it's not helping. The smaller one actually gives you a center crack. The larger ones actually almost again going back to the indentation type. And it's not surprising to expect that, because if you look at the center, that would be the calculation for the tensile stress in the center. If your diameter goes to very large, that means you need to have a very large force at the loading area to bring your stress up. If it is infinity, you need to have nearly infinity to make this a constant. And with a very large force, of course, near the loading area, you would have failed that area already. And therefore, when you have a large size for the Brazilian test, it's actually not a good idea. And in the literature, people have tried actually in concrete with cement to have the sample size of 3 diameter. 3 meters, in hope that they would try to figure out what is the size effect by going with the size bigger and bigger. But really, if you look at the mechanism over here and how the tensile stress would be depending on the P and the D, going with a large diameter of 3 meters is really not helpful. You are going from one mechanism to another one, and so you are really not in the valid region for Brazilian test interpretation any longer. And the dependence of the strength ratio, the dependence of the failure mechanism on the strength ratio was pointed out long ago by Dr. Charles Fairhurst in '64. And what he plotted over here, this N, you can interpret it as a strength ratio. So with N being 12, that's what we have more or less similar to sandstone. You have the tensile, he plotted as stress severity. In other words, how close you are to the failure envelope. So that's above 1. Now with N equal to 8, your strength ratio is decreasing. That's actually now below 1. In other words, now in the center, you will no longer fail in tension, but near the edge, the loading area, it's more possible to fail in the loading area when your N is small. So all these results, what I showed you is not really anything unexpected. We should have expected way back then. We know that way back then, but it's just that with a numerical code, we were unable to produce this type of failure mechanism and this kind of result. So I'll just show you the center crack development. You start, so the load is increasing in this direction. You start with a center crack, and then sort of develop near, because here is highly sheared, so the crack actually cannot just break through immediately. It will start to develop these crack bands, and then the band width would increase, and you would also have cracks growing from the outside and towards the center. And this is already post-peak, slightly post-peak. This is around the peak time. Okay. And for the indentation type of mechanism, you can see the microcrack starts from the loading area, and then they grow, and the crack eventually grows towards the center. And in between, you can see there's what I call the transition mechanism. That is where you have those microcracks start from the edge, from the top and bottom, but the center crack also more or less developed at the same time, together with with these microcracks, and that's perhaps the most interesting case because in this case, that if the failure mechanisms in this type of is like this, that's a case that gives you the most accurate tensile strength prediction. So the force displacement, there are fine details about how the failure mechanisms affect the Brazilian tensile strength. One of the things you can notice is that the tensile strength, this should be stress. The tensile stress in the uniaxial tension, so the tensile stress in this case increases with beta, but your force, the maximum force in Brazilian test actually decreases with beta. Again, that goes with the idea now your failure when beta is infinity is actually not governed by tension. It's governed by these shear events, and therefore it's more related to the compressive strength. That's why when you have the perfect brittle case, because in this case the compressive strength is the smallest. Therefore, in this case, the tensile strength from the Brazilian test is actually smaller than the tensile strength over here. In other words, if you are using Brazilian test, it's quite dangerous because the tensile strength from the Brazilian test is a function of your failure mechanism. So again, uniaxial compressive strength, tensile strength increases with beta, but the Brazilian tensile strength actually decreases with this beta. So I plotted the Brazilian tensile strength and counterplot with respect to beta. That's you can translate that to strength ratio and the particle and the sample diameter. So 1 is here, means they are equal, and so the Brazilian tensile strength either underestimates the tensile strength when the strength ratio is small, or overestimate, because when you have the center crack mechanism, really this equation. This equation, when you make this equal to the strength, this equation is only true for initiation. But you have progressed from initiation, and you still have to progress that far to get to the peak of the force displacement curve. So the tensile strength, if you are determining it from the peak force of the force displacement curve, you are actually overestimating it. So I will just show you a summary. My students have gone through many runs and try to get also a statistical distribution of these strengths. So this one's from uniaxial tension, and that's a case for elasto-perfect brittle contact laws. And as you can see, if you determine the tensile strength from the peak, it's underestimate the tensile strength. Now, when beta equals to 0.1, and that's the case I told you when the failure mechanism is in transition, and that's the case when the uniaxial tension, they actually agrees very well with whether it's crack initiation or peak strength from the Brazilian test. And the case when you have beta that's 0.015, that's when with the center crack, and the uniaxial tension gives you a strength that's much lower than the strength you would get from the Brazilian test. So we sum up everything over here. It's probably a little bit busy to read from this graph. The figure would, if you read, it tells you the ratio between the Brazilian tensile strength over the uniaxial tensile strength, and that decreases. It varies with the softening coefficient that translates to the strength ratio. And one means they agree with each other, and that's here. So the Brazilian test in the numerical simulation either underestimate or overestimate the tensile strength. It's only a narrow band with a suitable diameter that would give you the proper measure of the tensile strength. So in summary, we've developed a displacement softening contact model that overcomes the issue of the low strength ratio in DEM modeling. And the numerical result seems to justify the use of tensile tension cutoff for the failure envelope. And also, with now the strength ratio being realistic, we've observed a very interesting phenomenon in Brazilian test. And again, those phenomena have been observed in experiment a long time ago. And it's not that we are observing anything new, but we are, with a numerical simulation, of course, we have bring in very interesting insights to the behavior of Brazilian test. And we show that the Brazilian test, the tensile strength from the Brazilian test depends on the failure mechanism and also the size, the diameter of the sample. And it's, I would conclude it's rather dangerous to use that. All right, with that, I'll be ready to answer any questions you have.
Thank you very much, Haiying. Time for questions.
Thank you, Haiying. Really interesting results. Can you bring the slide where you show, I think, the compressive strength as a function of beta? You have a plot there. Because I'd like to go back, and I think, and you make the... No, you had plots where you just show the bonds being broken for three value of beta, if I recall correctly.
This one?
No, it was there were three sketches where you show the broken bond. Yeah,
one?
that one.
Oh, okay.
Yes, one. Okay. So you make a very interesting point that sigma c, the compressive strength, is related to the energy being dissipated at the bonds. And it reminds me of the fact that the strength, you could also view that as energy per volume. So that kind of can relate to that. Yeah. But in your simulation, if I understood correctly, you make sure that as you are changing beta, you are keeping the energy the same.
Yeah. So that's why only the number of crack matters.
Yeah, that's where I want to go back to that. It's not obvious to me that as you are going, because as you are decreasing beta, you're increasing the macroscopic compressive strength. But it's not obvious to me that the number of cracks is increasing. As you go from...
That's a plot, but if you read the number over here, I have the number written here.
Ah, okay. That's what I missed. Okay.
So the number, if you look at it, for 3D, the 2D is not significantly, well, it's still, you can say 5-6 times. Yeah. Right? the 3Ds from nearly 1,500 to 4,600.
Okay, so, thank you very much, because I was looking at the picture and it doesn't obvious, but right.
I tried to count.
And just to make sure that all the results that you have shown were calculated with the tau c over sigma c very large. Is that correct?
Yes, but we have actually our last few months has been going through adding the shear component. And the shear component, I should really actually thank the sponsors and also the hard work of my student. His name is Yifei Ma, so I wouldn't have, it wouldn't be here without him. Now, actually, we've done work with the shear bound changing. And shear bound changing in using two approaches. One is just make it bring down the number. So in shear, it's still elasto-perfect brittle. Second is to have softening in shear as well. But the global picture is not changing. Actually adding shear would bring down adding shear would actually bring down the strength ratio. If you look at, this is not working very well, Sonia, but so if you look at this ratio, if the shear bound strength is becoming comparable to the normal bound strength ratio, the overall strength ratio is actually decreasing. That was consistent with what we had a long time ago. Yeah.
Okay.
So the reason I didn't want to lay it out over here is because now you have so many parameters and the main things are sort of lost. Yeah.
I think we have to close unless last question because she has a meeting at 11:15.
Thank you, Haiying. It's really interesting. I wanted to ask, did you observe like the size of the process zone when, like, what would it be compared to the discretization?
Actually, that's an interesting question because I struggle on that one as well, how to figure that out. Well, if you look at, so in this case, you can think of it, a center crack develops immediately. Then, top and bottom would be, if there's any kind of softening bonds, you can characterize that as a process zone. But when I try to plot that, basically, what I see is process zone, softening bonds starting from the edge all the way down. They are very clean two bands, extending from the crack tip to top and bottom. So that means the process zone is at least, in this case, of 1/3 of the diameter. So that was quite surprising. I didn't expect that, but that's what we observed. In other words, in this type of material, the process zone is actually very large for tension, comparable to the diameter. Yeah.
Okay, as I said, we have to close. Please join me again to thank you.